Hi, this is a continuation of our lecture on statistics. Last time we looked at presentation of data and we looked at two types of graphical representation of data. We'll continue with our discussion of histograms, and this time we'll look at histograms of non-uniform width. Now consider this frequency distribution table. It has 25 to 35 9, 35 to 45 and 40 to 45 12, 45 to 51 and 50 to 65 3. Now look at the problems associated with directly plotting the frequencies as is without any changes to it. You will notice the problems associated when we start discussing the width of the class. The width of the class of this group is 35 minus 25, that is actually 10. In this case, the width of the class is 5, which is 40 minus 35. In this case also 5, this also 5, and this one, the width of the class is actually 15. So now if we drew histograms simply the way we did before, we would end up with graphs with width of 10 and the frequency or the height is 9, which would really not be true to what the data says. A better way to handle this situation would be to actually calculate the true frequency which can be associated to this group on average, considering its width of class. The reason as to why we need to do that is because in a histogram, the area of the rectangles are directly proportional to the frequency of the class. Now this would paint a very misleading picture if we do not correct for the difference in the width of class. The correct way to go about it is to first correct for the difference in width, and the way to do that would be to first look at the lowest or the smallest width of class and normalize basically all the data points down to that width of class. So for a class which has width 10, the data frequency of 25 to 35 group is 9. So 9 is the frequency for the width of class being 10. So for a class with width 5, this frequency can be changed to 9 by 10 into 5, which is equal to 4.5. So a true representation would be to have a rectangle with the width 10 but the frequency not equal to 9 but equal to 4.5. So these are corrected values for a histogram. Now because the class width here is 5, so this remains 5, this remains 12, this remains 1, and in this case it should be 3 by 15 into 5. So that is 1. This is equal to 1. But keep in mind that it might be again misleading here to say that this is 5 plus 5, this is 10, 10 plus 12 is 22, and 22 plus 2 is 24, and that we have actually missed some data points. That would be a wrong observation because we have not missed them, we have simply redistributed them and attributed correct frequencies according to the width of class, because as I said, the frequency is not equal to the height of the bar but actually directly proportional to the area of the rectangle in the case of a histogram. So let's just plot out the histogram and see what I mean. So again we start with the y-axis, and on that will be the frequency or the number of students. Right? And then we need to look at the minimum and the maximum. The minimum is 1 and the maximum is 12. So let's again go in gradations of 2. We have 2, 4, 6, 8, 10, and 12. Let's just have 14. Okay. And then on the x-axis, you have the weights. Right? Again, the data points here start from 25. So we'll draw a kink up until 25. This is 25. And we look at 25 to 35. But the minimum width of class is 5. So we'll move to 30, 35, 40. I finished labeling the axes here, and so let's just plot out the graph. So this should be 4.5. So that would be uh, somewhere around here, because this would be 5 and so this would be 4.5. And so from 25 to 35 we have 4.5. Sorry. And then you have 5. It should be slightly higher. Then you have 12 is up here. Then you have 1, which is exactly here. Then again 1. Now this one is from 50 to 65. So 50 to 65 you have 1. You see how this is a better representation than us drawing 9 here. I'll just by dotted lines show what this would look like if it were not normalized for changes in width. So the dotted rectangles represent what this histogram would have looked like if we had not corrected for the change in width of class. The problem with this would be that the height here is 9 and the width is 10. So this would be about 90. This would exactly be 90. And in this case, the frequency is 5 and the width is 5. So that is 25. So you notice how this is, and in this case, this is 5 into 12, which is 60. So you have 90 is to 25 is to 60, and you divide all by 5, you get 18 here, you get 5 here, and you get 12 here. So you see how the data is 12 and 5 correct. 12 and 5, the ratio in this is correct, but the corresponding ratio of this is exactly double of the actual frequency. So the frequency that you would get by not normalizing is actually wrong, and so therefore we need to correct for changes in class width, and so that's why we do it. So this is histograms with non-uniform width. Next we will look at frequency polygons. Frequency polygons are also drawn from continuous frequency distribution tables. and we can use the histograms that we drew for this table to actually come up with the frequency polygon of the frequency distribution. So this is the histogram of the frequency distribution in question. So let's see how we can draw the frequency polygon using the histogram of the data points given. What we have to do is to identify the midpoint of each edge. So the midpoint is approximately here, and in this case it's here, it's here, it's here, and it's here, right? So, and simply join these points with straight lines. And apart from this, join this to the midpoint of another fictitious group, which obviously has the frequency 0, but anyways join it to the x-axis at the midpoint of a fictitious preceding group. I'll tell you the advantage of doing that. And in the same case, and as this one, join it to a succeeding fictitious group to the midpoint of the succeeding fictitious group. So you do this. So the advantage of doing this is that on doing this, the area of the frequency polygon turns out to be equal to the area of the histogram for the same data. That might be useful in some cases. Also, name the points that we have identified, like A, B, C, D, E, F, G, and so therefore A, B, C, D, E, F, G is the frequency polygon required. Now, there is another way to draw the frequency polygon without the help of the histogram which is associated with the frequency distribution. For that, we would require a concept of something called a class mark. Class mark is nothing but upper limit plus lower limit by 2. In fact, it is manifested in the frequency polygon that we made here also. These midpoints are precisely what you mean by class mark. So let's identify the class mark for each of these classes. The class mark for this would be 30 plus 35 by 2, which is equal to 32.5. In this case, it will be 35 plus 40 by 2, which is equal to 37.5. And similarly, this is 42.5, this is 47.5, this is 52.5, right? And so that's what class marks are. So instead of drawing the histogram, what you can do is simply get the coordinates of all of these points by using the class mark and the frequency, where the class mark becomes the x coordinate and the frequency becomes the y coordinate. This is the x coordinate and this is the y coordinate. That's what you see here also. B is the x coordinate, that is, this is approximately 32.5, and the y coordinate is 9. So that's how you make the frequency polygon without using the histogram. And this is what the frequency distribution looks like. Frequency polygon looks like without the help of a histogram. In this case also, A, B, C, D, E, F, G is the frequency polygon. So this is all we had to say regarding graphical representation of data. We will stop here for this lecture, but another major portion that is left is the measurement of central tendency, and we'll cover that in the next lecture. For now, this is all. Thank you.